Good morning, folks. This is Todd Coburn of Cal Poly Pomona with lecture 22 of Arrow 4080. Today we're going to look at how to do nonlinear analysis in NASTRAN. Okay, let's take a look at how that works. Now, before we get started looking at the details of nonlinear analysis with NASTRAN, let's take a look at what this actually means. Since the beginning of our journey into structures, and actually all engineering, we've been making a number of assumptions. One of those assumptions is the assumption of small displacement. Another one is the assumption of a linear stress strain curve. So we could say, well, actually we've got two major assumptions. One of them is that our displacements are tiny. That means if we have a beam like this and we apply a load, it hardly moves. This number is really small on a 10-inch beam, and this is just a wild number out of the air, maybe 1/10 of an inch. If we have a 10-inch long beam and it actually deflects 2 or 3 inches, that's large displacement. In fact, if it displaces a 1/2 inch, that might be large displacement. Okay? The other assumption, so anytime, and remember the reason we did this is we had simplifications of our trig as we looked at the slope of this thing. We made simplifications on trig that laid the groundwork for simple analysis but just don't apply if our displacements are larger than that. The other major assumption we make is that of material nonlinearity. If you remember back to our stress strain curve, it has a linear portion and a nonlinear portion. And whenever we're doing analysis, we're basically assuming that this E, the slope of that, is here in the linear range. We know the actual E is tangent of this, and it goes to 0 as we get out here. So there are two things. This is called large displacements. That's one kind of analysis, of nonlinear analysis, and the other kind is material nonlinearity. That means all the analysis we normally do and the NASTRAN does for you is all assuming that your E doesn't change. You're down in this part of the stress strain curve. When we go to material nonlinearity, you can actually put in the stress strain curve and get the effect of the nonlinear material. But these are the two major kinds of nonlinear behavior. Okay? So first let's take a look at the basic elements of a nonlinear NASTRAN deck. Take a look at this little excerpt from a NASTRAN deck. You'll notice we have a few cards highlighted here. The first thing we're going to need, remember normally we're using a solution 101, or we call it a solution static. Solution 106 calls out a nonlinear analysis. You can do both material and large displacement analysis with that. You'll notice the rest of the executive deck and case control deck is the same, except that we have an additional card, NLPARM. That's going to tell us what nonlinear parameters we're going to use. And actually all that does is identify the ID number of the card that's in the bulk data deck that will tell us how the nonlinear analysis is going to be behaved. And then down here in the begin bulk, we're going to get two cards. One of them is our NLPARM card. You'll notice that the ID called out here in the case control has to match the ID called out in that NLPARM card, and also it has more information that we'll look at in a minute. And then the last card that's different is this parameter large displacement. Now we can use a few different things, 1, 2, -1, and other things. We'll look at that in a minute. But basically, these three cards, we switched our solution sequence to 106. We added a case control card, NLPARM, to call out the parameter card, the NL parameter card that we're going to use, and then we use that parameter large displacement card. Okay? Those are the only three differences. Everything else about your model will look the same. Sound pretty doable? Okay. So if we take a look at our first one, our solution 106, we find that this is just going to call out the nonlinear behavior. We said that we don't really need this additional thing, but that's what that card does. Next we have that NLPARM card. The NLPARM card, once again, is just calling out the ID of the parameter card that's going to tell how the nonlinear analysis is going to be performed. And then we get to the meat and potatoes where we have our NLPARM card. The NLPARM card does a number of things. We've got the name of it, we've got the ID, and then you'll notice the number of increments. This is telling NASTRAN how many increments it's going to use. So the way it works is, remember, our basic theory for doing analysis was assuming small displacements. We're really not going to change that when we're doing a nonlinear analysis, but what we're going to do, let's go back to that cantilever beam example. Let's say we have a load of 1,000 pounds that ended up giving us what we consider a large displacement. What this is going to do is we're going to take that load and we're going to divide it up. So if we say, hey, if 1,000 pounds cars is too big of a displacement so that we violate the small deflection assumption, all we got to do is divide it up by, let's say, 1,000. Let's put on 1 pound and see the deflected shape. And then 1 pound, see the deflected shape. And then 1 pound, see the deflected shape. So we go 1, 2, 3, 4, 5, all the way down to 1,000 pounds. Or if you're impatient and don't have all day for this thing to run, maybe you'll say, I'm going to allow it to do 10 iterations, which means you'd have 100 pounds, and then another 100 pounds, and another 100 pounds. What that's doing is it's basically giving you a bunch of smaller solutions. When added together will give you the total solution so that you don't violate that. Obviously, if you choose your number of increments to be too big, then you're actually going to have some error in the analysis, just like you did initially. But the larger this number is, the more accurate your number will tend to be. And at some point, you're going to find that your number doesn't change much when you break it into smaller and smaller pieces. And that's one thing that you could do to study how this card works. And that is just to practice with the same model, play with that N-ink card and divide it up into 2, 3, 5, 10, whatever number of increments, and see how it changes your answer. You'll find for small changes it will change it, and then once you get past a certain point it shouldn't change a whole lot more. And then there are a whole bunch of things calling out what the method and step size and other little things that you can put in to this card. We're not going to deal with any of those. We're just going to use these first two fields, which means the ID that matches the NLPARM card and the case control, and the number of increments, or the number of pieces we're going to divide that load into. So 100 pounds divided by, if we do 10, then that'd be 10 pounds a piece. If it's 10,000 pounds divided by 10, it'd be 1,000 pounds each. Got that? Keeps it pretty simple, and it's good enough for our work in this class. The next thing is our large displacement card. This is the large displacement card. You'll notice I said we're going to set that to 1, which we're going to have large displacements and follower forces. We can actually turn it to 0, which means they're not included, and that may revert back to like a static analysis. I'm not totally sure. I should probably play with that. Number 2 gives us non-follower. So follower forces basically means your force is moving with the load rather than staying where it was initially. These are all going to give us little variants. We're not going to officially play with these in our class. You're welcome to play with these as you like. We're going to just stick with the large displacement parameter being 1 for our purposes, okay? So the next one we're going to look at is nonlinear behavior for materials. And if we have that, you're going to notice here that we have exactly the same cards. We still have the Solution 106 card. We have the NLPARM card with an ID. We have an NLPARM card in the bulk data section with the same ID and the number of steps we want, and the large displacement card. The difference here is we now are going to call out a material. So you'll notice that the whatever elements we have are calling out probably mat1, material 1, which gives a modulus elasticity. Remember the modulus elasticity given out in the material card. So we're talking about this material card here, and the modulus of elasticity tells us what this initial slope is of the stress strain curve. Then you'll notice we have other things that are telling about what kind of loading we're having and some other information, okay? So we're going to take a look at what the rest of these things do. We can actually, we'll look at that on the next slide, but basically what this card is going to do, you'll notice this 10 to the 6 is telling us what the initial slope is of our stress strain curve, or our E, and this card is going to tell us what the rest of this curve looks like. It could be fully plastic or off at some slope or something else. Okay, we'll see how that plays out on the next slide. So taking a closer look at that second material card, you'll notice we had two cards. One of them was the a Mat 1 card, which basically tells us what the initial slope is of the stress strain curve. What the initial slope is, okay? Now actually we're going to use, this is, so you'll notice when we have an element it's calling a material card, you'll notice these IDs are the same. What that means is if you have like a C-bar card that calls out this ID that has uses a material ID, or a P-bar card that uses a material ID of 1, then basically it activates both of these cards. The first one tells what the initial slope is of the stress strain curve. Okay? The second one, the rest of these tell you more about the stress strain curve. We're not going to dive into all these parameters deeply, but basically we're going to call out plastic, meaning we want plastic analysis. We're going to leave that field in there blank. Then we have plastic. Go ahead and set these parameters the same way I have them. And then we're going to call out this. What this is the yield point. So what it's saying is we have a modulus given in this material card. That's giving the slope of the stress strain curve initially. And what this field is doing is telling us at what stress level is the yield, 20 KSI. And then the rest of this card tells what happens at that point. Since we called out this third field here that we left blank is the one that allows us to call out a table where we put in a set of values. If we use those table entries, you can call out, instead of just having the initial stress strain curve, you can call out a table of values that define the rest of the curve. We're actually not going to do this in this class. You're welcome to play with that, but we're not going to do that. What we're going to do is leave that blank and use this. What that does is define fully plastic behavior, which means the first material card calls out the initial slope, the second one calls out the yield, and then it's fully plastic after that, which means it's basically got a 0 slope, which means the E at that point is 0, which basically means that when NASTRAN runs its analysis, let's say we have a truss that we run nonlinear, let's say it's on rollers, and we apply a load, and what'll happen is each of these members will pick up load using an E of 10 million until the stress gets above the yield point. In this case, it's 20,000. On the last slide, it was 50,000. So at 20,000, from then on, that rod or bar will continue to hold that E, whatever load it had before, but it won't add any more load to that. And it basically will go as if it buckled, or as if it just kept on yielding and yielding, like we see when the stress strain curve gets totally flat. So this is a kind of a nice, easy way to implement plastic behavior, going fully plastic, similar to what we learn in plastic analysis of 3271. Okay, so when we do this, if we were to do material nonlinearity, we would just call out the same material card ID as the rest as our materials are. You're still going to need that Mat 1 card. We're going to call out a blank for the next one because we're not going to use table entry. We're going to call out plastic, set these parameters, next three parameters the same, and then put in your yield point, 20,000, 30,000, whatever it is you want to yield over to fully plastic behavior. If you want to go all the way up to FTU and then yield over, rather than just going above that, then you could certainly do that. So that summarizes how we implement nonlinear behavior. We're going to look at one additional card to add it to our repertoire, and here it is. This is called the Pbeam L. Now I've been encouraging you guys to use a C-bar card, and rather than a beam card, C-beam card. But this is a Pbeam L card. One of the cool things about this is it allows you to find a shape. Notice that this card, you have a whole bunch of run-on things with all these dimensions. If we go to the next slide, we see that here's the little detailed parameters. And the next slide, basically what this allows us to do is call out a section. Like let's say we have an I section. If our I section is symmetric and follows this, we can actually use the Pbeam L to put in exactly our section without drawing our section. We could use it for symmetric C channels, H's, other C channels, U's, all kinds of sections. All of these sections can be used, and what that does, instead of having to calculate properties for those sections, you'll notice this looks like we have a stringer with effective skin. You can just put in the dimensions in your Pbeam L card, and it will calculate all the stuff that you need. Now, we're not going to do anything with this card in this class unless you feel like it, but I wanted to introduce that card. Maybe in future classes I'll give you an assignment where you get to play with that and see how that works. Now, what you've already started doing when you're using FEMAP, we talked about this, how you can go and draw the shape, let FEMAP calculate your properties, and then it will create a card with those properties. So if you want to use that feature, I recommend using that feature since we are diving into FEMAP. But the amount of things that we can learn in this class are actually somewhat limited, and therefore we're not going to go beyond that. So we learned about two kinds of nonlinearity. We learned about material nonlinearity, and we learned about deflection nonlinearity. And that is the way that we can implement that. Now, you're probably thinking, wow, this looks simple, but how does it work? The best way to do that is with an example. And yet, you guys are already armed with everything you need to run this effectively. So if you look at homework 22, you will find that it walks you step by step into how to perform a nonlinear large displacement analysis of one of your homework problems. Give it a shot. Bring any questions to his office. Enjoy.